Next, let's take a small sidetrack that includes some really important physics. We know that a wave changes in both time and space. Are those changes related? So what I've got written on the screen is the equation for a sinusoidal wave which is traveling to the right. We know from earlier that if we take the derivative twice with respect to time, we get the transverse acceleration. So this is AY, is the second derivative of y with respect to time. I'm going to call this equation equation 1. We've already established how the wave changes with respect to time. Well, let's do the same thing to see how the wave changes with respect to space. Let's take the second derivative of y with respect to x. So we do die by x. We take the derivative with respect to x, which means we keep t constant, of die by x of the y equation, which is a times cosine kx minus omega t plus phi. Okay, so let's get stuck in this derivative. Let's deal with this bracket part first. I think I'll try and do this over here on the side. So the first thing I'll do is I'll take my a outside because that's a constant. So I've got the derivative with respect to x, cosine kx minus omega t plus phi. The derivative of cosine is negative sine kx with the same argument. Then I have to apply my chain rule, which means I multiply by the derivative with respect to x of kx minus omega t plus phi. The derivative of kx is k. The derivative of omega t is 0. And the derivative of phi is 0. Remember, we're taking time as constant, omega is constant, and phi is constant. So then that gives us minus a times k times sine of kx minus omega t plus phi. Okay, so that means now I'm doing die by x, the partial derivative with respect to x of minus a times k times sine kx minus omega t plus phi. Take my a and k outside and my minus sign. So I'm doing the derivative with respect to x of sine kx minus omega t plus phi. Got minus a times k. The derivative of sine is cosine. With the same argument. And then my chain rule says I have to do the derivative of the argument as well. And that's going to give me just k. So I've got minus a times k squared times cosine kx minus omega t plus phi. And this is my second derivative of y with respect to x. So this is about the spatial change. I'm going to call this equation equation 2. You might notice here that the equations look kind of similar. They both have cosines, they both have negative amplitudes. One has an omega squared and one has a k squared. They look pretty similar. Let's see how they're related. So now on my next slide, I've just got my equations typed up a little bit nice and neat. I'm going to solve both of my equations for the cosine term. So for my top equation, I'll divide both sides by minus a omega squared. So cosine kx minus omega t plus phi equals minus 1 over a omega squared times the derivative with respect to time twice of y. I just left out my as a function of x and t because I don't want the slide to get too full. Okay, I'm also going to write my equation 2. I'm going to solve that one for cosine. Cosine kx minus omega t plus phi. This one's minus 1 over a k squared times the second derivative of y with respect to x. So my cosine has to equal my cosine. So these two terms have to be equal. I'm going to set those equal and see where I get. So minus 1 over ak squared times the second derivative of y with respect to x equals minus 1 over a omega squared times the second derivative of y with respect to time. Okay, I notice I've got a minus sign on both sides, so they cancel. I've got an a on both sides, so they cancel. And then I'm going to multiply both sides by k squared. That's going to give me that the second derivative of y with respect to x is equal to k squared over omega squared times the second derivative of y with respect to t. Okay, that k over omega, that might ring a bell for you. V equals omega over k. That's our wave speed. That means that k squared over omega squared is 1 over v squared. Okay, now we're ready to write down our general result here. The second derivative of y, which is a function of x and t, with respect to x, is equal to 1 over v squared times the second derivative of y, which is a function of x and t, with respect to t squared. This is a pretty important equation. This is the general form for all traveling waves. That's actually a pretty important result. We derived the expression for a sinusoidal wave that was traveling to the right, but it is true for any wave at all that's traveling. Within these waves, there are two classifications that deal with amplitude. If the amplitude of the wave is a lot smaller than the wavelength, that's called a linear wave. If the amplitude is bigger than the wavelength, that's called a nonlinear wave. In both cases, though, if y fits this equation, then it is a traveling wave. The disturbance will propagate as a wave along the x-axis. In our class, we'll only study linear waves. If you go into higher physics, you'll study some nonlinear waves, which is really kind of neat and fun. Okay, so any y that fits this equation describes a disturbance which propagates as a wave along the x-axis with constant speed v. It doesn't have to be sinusoidal and it doesn't have to travel to the right. The really interesting impact of this, what I think is really cool, is that Maxwell, so James Clerk Maxwell, most of our course is actually about him. So Maxwell actually used this description, or this equation, and he used that equation to prove that light was a traveling electromagnetic wave that had a wave speed of v, which was equal to c. So let's get that in a note because it's actually pretty important. So Maxwell used this description to prove that light is a traveling, and we're going to come back around to this later on in the course, EM wave with speed v equals c equals 3 times 10 to the 8 meters per second. That was pretty revolutionary. That hadn't been proven up to that point. So I kind of think it's cool that a math equation proved something about the nature of light. That's pretty awesome.